Okay, in this presentation we are going to look at the moment generating function of a binomial random variable. So this is part of the random variables section of a probability and statistics module. So this one's actually straightforward enough really. There's one mathematical identity that you have to remember to use, and if you use it properly, this one actually is fairly straightforward. We'll come to that shortly. The moment generating function of a binomial random variable, let x be a binomial random variable with the standard parameters n, which is the number of independent trials, and p, which is the probability of the success in each trial, the standard stuff. Derive the expression for the moment generating function mgf of x. Great. So just a quick recap on the moment generating function. Let x be a random variable with cumulative distribution function f of x. The moment generating function mgf of x is denoted as follows. It is the expected value of e to the tx, the exponential of tx, okay? Provided this expectation exists for t in some neighborhood of 0. That's an important little matter, but we won't go into it in this video. Now, binomial random variable is the discrete random variable. So we're going to use the first of these two cases. So it's the summation of this expression here, etx times the probability of x. So that is essentially the probability mass function. Okay. So this is not too different from calculating the expected value of a discrete random variable. In fact, actually that's exactly what it is, more to the point, but it is the expected value of the exponential of tx. Okay? So there's a continuous random variable form there, which I won't go into in this video because we'll just try and keep this one short and sweet. Now, just a remark, the probability mass function of the binomial random variable, just in case you need a bit of a recap on it, it is this expression here. The probability of x equal to k, where k is some integer between 0 and n, 0, 1, 2, 3, all the way up to n. That is n choose k, the binomial coefficient of n and k, times the probability of k times 1 minus p to the power of n minus k. Okay? So there we have it there. Those are all of the components there. Just why I actually deliberately included it here is just to actually sort of remark on the general structure of it. We have the binomial coefficient, we have p to the power of k, and we have 1 minus p to the power of n minus k. Okay, so yeah, that's the general structure of it there. Now, the reason why that is important, because I want you to sort of remark upon the similarity between the structure of that expression and the structure of this expression, particularly what is on the right-hand side. We have a summation there from k equals 0 to n of n choose k, the binomial coefficient of n and k, a to the power of k times b to the power of n minus k. Okay, and what does that mean? What is that equal to? That summation is equal to a plus b to the power of n. So essentially this is the trick. Remembering to employ the binomial expansion expression when we are trying to solve this. Then it turns into a very straightforward question very quickly. So let's go into it here. Algebraically rearrange our expression to make use of the binomial expansion formula. Okay, so m of t subscript x for the random variable x is the expectation of the exponential of t on t times x. Okay, so that is using the probability mass function. I'll just go back here a second just to use this expression here, the first bullet point. Just to remark upon that, for a discrete random variable PMF, we're using that first bullet point there, okay? The exponential of tx times the probability of x. In this case, it'll be probability of k. So, or probability of t actually. So what we have here is the e to the power of tk times n choose k times p to the power of k times 1 minus p to the power of n minus k. Okay, so what we're going to do is try to restructure this in a format that suits the binomial coefficient. And essentially what we're going to do there is there's 4 terms in the second line there, in the summation on the second line. We are going to combine the first and the third term, which is e to the power of tk and p to the power of k. They're both expressions with respect to the power of k, okay? So if we combine them, we get p times e to the power of t to the power of k, okay? We have n choose k there, the binomial coefficient, and we have 1 minus p to the power of n minus k. The summation index is the upper and lower limit of the summation index is k equals 0 to n. That's fine as well. So in fact, we're actually done. This is the bit where we actually get to employ the binomial expansion. So the expression inside the summation is a binomial expansion. Recall that the general form of the binomial expansion is a plus p to the power of n equals the summation from k equals 0 to n of n choose k times a to the power of k times b to the power of n minus k. So what we're going to do here is set a equals p to the power, p times e to the power of t, and b is equal to 1 minus p. We're home and dry because literally that is what we have to do. So that is the trick there. We're actually done now. Okay, so just going back to our expression here, we have a is p times e to the power of t. B is 1 minus p. So a plus b to the power of n is p times e to the power of t plus 1 minus p to the power of n. And we're done. That's it. That's all we have to do. So just a quick recap on the key thing there, the binomial expansion. If you have that in your ready to go in your head, when you're faced with this, you're done. You get this out the door very quickly. Okay, we'll leave it there.